Section 5.4, Special Factoring Techniques. There are three types of factoring problems that we want to look at in this section. And the first one comes from our look at special products back in section 4.6. In 4.6, we had a rule that said if we have the product of a sum and difference of the same two terms, the result would always be the first squared minus the last squared. Now we're going to turn that around. And we're going to say if we see something that looks like this, then that must be how it factors. If we see what? A difference of squares. So the first special factoring we're going to look at is a difference of squares. And in our book, she has a brown box for us here at the beginning of the section, page 353. Factoring a difference of squares, brown box just above the center of the page. And she has the same rule in this brown box as I have on the board right now, except she has X's and Y's. I have F's and L's for firsts and lasts. And it's very simple. If I see a difference of squares, let's say x squared minus 25. When I see this binomial, one thing I'm going to check for is this a difference of squares? Does it look like this? Well, x squared is the square of x. 25 is the square of 5. And so this is a difference of squares where the first is x, the last is 5, and so this will factor as x plus 5, x minus 5. And it is as simple as that. It's recognizing that pattern. You have a handout on which I want you to memorize those first 20 perfect squares along with the first 10 perfect cubes, which we'll also be using in this session. But you've got to be able to spot these perfect squares and here in a bit some perfect cubes. So let's do some more. A difference of squares. There's our rule. Let's head over to the homework. Grab number 8. I see a binomial, so one thing I ask myself is this a difference of squares? Well, t squared is the square of t. 36 is the square of 6. And so this is a difference of squares, and it will factor as the first plus the last times the first minus the last. And of course we can always check this by multiplying this back together. I'm going to go ahead and FOIL this out, although we could use our special product rule. But if I FOIL this back out, the first is t squared, the outside minus 6t, the inside plus 6t, the product of the last, watch your signs, minus 36. Combine like terms, and those linear terms subtract out. And that does return me to that original binomial. Let me just make one up here. Let's consider, let's say, x squared plus 25. And the instructions say factor. Now, how does this factor? Is this a difference of squares? No, this is a sum of squares. So we know it's not going to factor like this, because that will give me a negative 25 back at the end. If I FOIL this back out, I get x squared minus 25. Okay, what about x plus 5 times x plus 5? That will certainly give me a positive 25, but what else? When I do my outside and my inside, they're each going to be 5x. So when I FOIL this back out, I'm going to have a middle term. So that doesn't work. If I were to make them both minus, which these two at the bottom you should recognize from our special products in section 4.6. These are squares of a binomial. If I FOIL out this bottom one, I end up with a minus 10x in the middle for my outside and inside once I combine like terms. So none of these are the way this factors. How does a sum of squares factor then? It doesn't. A sum of squares is prime. 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 Yet invariably I have students try to factor this on a quiz or a test. A sum of squares is prime. This is that second unforgivable mistake in this course. If you try to factor a sum of squares, a sum of squares in and of itself is prime, cannot be factored. And it's that simple, it's that straightforward. Look at number 14. The instructions read, factor. Is that a difference of squares? I've certainly got squares, the square of k and the square of 7, but is this a difference of squares? No. This is a sum of squares. So we're done. A sum of squares is prime. Now very careful, look at number 16. In number 16, we have a sum of squares. This first term is the square of 3x. This last term is the square of 9. This is a sum of squares. But what do we know we should always do first? First things first when you're factoring. Always, always, always look for a greatest common factor first when you're factoring. And between these two terms, there is a greatest common factor. I can factor out a 9. And that will leave x squared plus 9. Now, will this factor any further? No, it won't. I've factored out the greatest common factor, and what's left is a sum of squares. That sum of squares is prime, but I've already factored this binomial once. The original binomial is not prime. I was able to factor out a 9. So there's my final answer. Notice your brown box here at the top of page 354, a sum of squares. It says if x and y have no common factors, then a sum of squares, x squared plus y squared, cannot be factored using real numbers. That is, x squared plus y squared is prime. She said, if there's no greatest common factor, then a sum of squares is prime. If there is a greatest common factor, pull it out and be done. But in and of itself, a sum of squares is prime. Number 20. I see a binomial. I see a subtraction. Is this a difference of squares? But I'm getting ahead of myself. First things first. Always, always, always look for a greatest common factor first before you do anything else. I can factor out an 8. If I pull an 8 out of each term, it will leave 4a squared and minus 1. Now, can this be factored any further? Is this thing in parentheses factorable? Why, yes. It is a difference of squares. This first term is the square of 2a, and 1, of course, is the square of 1. So we've got our greatest common factor. Don't forget your 8. And then this difference of squares, this binomial, will factor further. as the first plus the last times the first minus the last. Now this is factored completely. Let's have a go at number 22. Do you have your handout handy? These powers should be memorized. Or perhaps do you already have them memorized? Either way, we need to get them memorized, and either way, we need to recognize that this is a difference of squares. 361 is the square of 19, so this first term is the square of 19q. And 400 is the square of 20. So this is a difference of squares, and it will factor as the first plus the last times the first minus the last. And if you've done these before, it may be the case that you were taught to put the minus up front. It doesn't matter. This is the same answer. I'm just swapping the two factors. Exactly the same answer. It doesn't matter if you use the addition first or the subtraction first. All right, I've got one for you to try. Number 26. Go ahead and pause and then come back when you're done and we'll compare answers. We recognize this binomial is a difference of squares because this first term is the square of 6y. If I square 6y, I get 36y squared. And this last term is the square of 11z. So I do have a difference of squares, and it will factor as the first plus the last times the first minus the last. These can always be checked by foiling them back out. How'd you do? Now let's take a look at number 44. It has a little something extra in it. Number 44. Let me rewrite that a little lower on the board so I have room for my clouds. I see a binomial, and one question I need to ask myself is this a difference of squares? What can I square that would give me k to the fourth? K squared squared is k to the fourth. So k to the fourth, any even power is going to be a perfect square. K to the fourth is a perfect square. 81 is a perfect square. It is the square of 9. And so this will factor as the first plus the last times the first minus the last. Are we done? Is this factored completely? The instructions read factor, which always means factor completely. Is this factored completely? Well, I have a sum of squares here in this first set of parentheses. That can't be factored any further because what? A sum of squares is prime. But what about this guy? This is a difference of squares. The square of k and the square of 3. So there's nothing I can do with this sum of squares up front. We're stuck with him. He's prime. He doesn't factor any further. But this second binomial will factor further as this first plus this last times this first minus this last. And now this is factored completely. And do you understand what we're doing? To factor completely, it's just like doing a prime factorization. We factor until we can't factor anymore. This binomial factored into these two factors. This one was prime, so it came on down, but this one was factorable further. And so it's like doing a factor tree, and we factor until everything we have is prime, until everything we have cannot be factored any further. And that's how we know when to stop. So that's a difference of squares. There was another rule back in section 4.6 which said if I have the square of a binomial and multiply that out, it will result in the first squared if I have the square of a binomial. That will result in the first squared, in this case plus, double the first times the last, and plus the last squared. We said if that happened to be minus, the only thing that changes in my answer is my middle term will be negative. Now we're going to turn this around and do it the other way. If I have a trinomial that happens to look like this, then I know how it factors. And this thing on the left, this is just our rule for 4.6, but it's turned around backwards. This trinomial here on the left is called a perfect square trinomial because it is the perfect square of some binomial. It's a perfect square. Just like 81 is a perfect square, 49 is a perfect square. Any trinomial that looks like that is a perfect square trinomial. She has this for you in the book on page 355, brown box just below the center of the page. She gives it as two separate rules, where I use plus minus notation. She has x's and y's. I have f's and l's for firsts and lasts. So we need to be able to recognize perfect square trinomials. The instructions read factor. Now, there's nothing wrong. This looks just like a 5.2 problem, where I would say, oh, I've got a trinomial, leading coefficient's 1. If it factors, it will factor as a pair of binomials, each starting with x. Right here, signs are the same. In fact, right here, they're both positive. And I'm looking for two numbers. I'm looking for two numbers whose product is 9, whose sum is 6. Can you think of any two numbers that multiply to 9 and at the same time they add up to 6? How about 3 and 3? So we could do this without this formula, but here again, the idea of recognizing perfect square trinomials is going to be very important to us in our next class, next semester in college algebra, in algebra with apps. Recognize also I could write this answer as x plus 3 quantity squared. That just says two factors of x plus 3. Either way, we want to be able, however, to recognize a perfect square trinomial. And I'll show you at least one example today where that's especially true. How do I recognize a perfect square trinomial? Well, it's got to look like this. It has to start with a square, and it has to end with a square, and the thing in the middle has to be double the first times the last. Now, is that true of this trinomial? Well, it starts with a square. It starts with the square of x, and it ends with a square. It ends with the square of 3. So now I have to ask, is this term in the middle 2 times the first times the last? Is this thing in the middle 2 times x times 3? Yes, it is. So this is a perfect square trinomial. Well, then I know how it factors. It factors as the first, and in this case plus, the last, quantity squared, and I'm done. Can I use the methods from 5.2 and 5.3 to work Perfect square trinomial problems? Yes. Do I have to know how to factor a perfect square trinomial at this point? Not really. Should I know how to factor and recognize a perfect square trinomial? Oh yes, absolutely. And so we're going to do a few more. Let's try number 54. This is another reason you need those powers from your handout memorized. You need to be able to spot these perfect squares from a distance. In fact, you'll know when you've memorized that sheet sufficiently when you're driving down the road and on the license plate ahead of you, you see 343 and you go, hey, that's a perfect cube. That's the cube of 7. And then you go, oh crap, what has Fox done to me? That's when you know you've got it. When you look at the clock and the clock says it's 2:25 and you go, hey, that's 15 squared. And you just shake your head because you know it. That's when you know that you've got it. I see a trinomial. And what jumps out at me is it starts with a square and it ends with a square. Well, looky here. This trinomial starts with a square, the square of x, and it ends with a square, the square of 5. And then you say, I wonder, is this term in the middle, ignoring the sign, is this term in the middle double the first times the last? Why, yes, it is. Well, then this is a perfect square trinomial. I know how that factors. It'll be the first, and in this case minus, the last quantity squared. And that's that. Could I use the methods from 5.2 and say, pair of binomials, each starting with x, signs are the same, both minus, product of 25, sum of negative 10, it's got to be minus 5 and minus 5? Sure. But what we want to practice in this section is recognizing these perfect square trinomials. So let's keep going. Number 58. Now this is not a perfect square trinomial. 3 is not a perfect square. But I'm jumping ahead of myself, right? Because the first thing I want to do in any factoring problem is check for a greatest common factor. Is there any greatest common factor among these three terms? You should know your rules of divisibility well enough by now to recognize that all three of those coefficients are divisible by 3. If I factor 3 out, it will leave me a y squared plus 3 goes into 48 16 times, 16y, and plus, let's see, 3 goes into 19 6 times, remainder 1 is 12, makes that 64. The mumbling you just heard was me doing a long division quickly in my head. You do whatever you've got to do to get that 192 divided by 3. The question now is, will this factor any further, or are we done? Well, looky here. This trinomial starts with a square and it ends with a square. It starts with the square of y. And it ends with the square of 8. I wonder, is this term in the middle double the first times the last? Yes, it is. And so this thing in parentheses is a perfect square trinomial. Don't forget your greatest common factor out front. And then this perfect square trinomial will factor as what? The first, and in this case plus, the last quantity squared. All right, let's do number 66. First things first, let's look for a greatest common factor. Well, even before that, let me make sure I copy the problem correctly, right? Let's look for a greatest common factor. Among these three terms, well, they don't have any letters in common, all three of them. What about the coefficients? Well, 9 is nothing but 3 times 3. 3 won't go into 16. So no, there's no greatest common factor to factor out. I have a trinomial. When I see a trinomial, I want to look and see, does it happen to be a perfect square trinomial? Well, looky here. It starts with a square. It starts with the square of 3t. And it ends with a square. It ends with the square of 4r. I wonder, is this term in the middle double the first times the last? Yes, it is. It is, and so this is a perfect square trinomial. Makes my work very simple. This is going to be what? The first, and in this case plus, the last, quantity squared. Could I use section 5.3 and end up getting 3t plus 4r, 3t plus 4r? Sure, and there's nothing wrong with that. But my goodness, in this one, if I recognize it, it makes my work very quick and easy. And next semester, we're not only going to need to recognize perfect square trinomials, we're going to have to understand them well enough to create perfect square trinomials. So this is essential practice. Number 72. First things first, factor out a greatest common factor. Among these three terms, the greatest common factor is x squared. If I factor out x squared, it will leave me 4x squared plus 2x plus 1. Are we done, or will this factor further? Well, looky here. It starts with a square, the square of 2x, and it ends with a square, the square of 1. I wonder, is this term in the middle double the first times the last? Double the first times the last would be 4x. So no. No, this is not a perfect square trinomial. Okay, well, then maybe this will factor like section 5.3. It's got to be a couple binomials, each starting with some x term. Signs are the same, in fact, they're both plus. The only way for a 1 to fall apart is 1 and 1. So how does this 4 fall apart? Is it 4x and 1x? Well, check your outside and inside. Outside is 4x, inside is 1x, that totals 5x. That doesn't work. Putting the 4 over here won't give me anything different, will it? It'd still be those same two factors. Well, maybe 4 is 2 times 2. Well, if that were true, this would have been a perfect square trinomial, wouldn't it? Something times itself. But check the outside and inside. What do you get? 2x plus 2x is 4x. That doesn't work. I think we've tried everything. But just to be sure, our AC method will tell us I'm looking for two numbers whose product is what? A times C. 4 times 1 is 4, and whose sum is 2. Is it 1 and 4? Nope. Is it 2 and 2? Nope. And those are all the factor pairs of 4. This won't factor any further. That thing in parentheses is prime. So do I write prime for my answer? Certainly not. You've already factored once. You've already factored out a greatest common factor. This is factored completely then at that step. Now let me show you a good one where it's good to know how to factor a perfect square trinomial. if you look at this problem and say, I think I'd like to use section 5.3, well, I don't know what I'd think about that. Maybe you're a glutton for punishment. No greatest common factor to factor out. In fact, 121 is what, 11 times 11? 11's not a factor of 81. So there's no greatest common factor. Now, if you want to sit here and try 5.3, help yourself. And it may be the case that we have no choice but to do this with the method of 5.3, but I hope that's not the case. Well, looky here. This trinomial starts with a square. It starts with the square of 9z. And it ends with a square. It ends with the square of 11. I wonder, not only do I wonder, I really hope that this thing in the middle is double the first times the last. 2 times 9 is 18, times 11, 198z. Nice. This is a perfect square trinomial because the thing in the middle is double the first times the last. And so this will factor very easily as 9z, in this case minus 11 quantity squared. And we're done. If I can recognize a perfect square trinomial, it makes quick and easy work out of some of these problems. Now there's one more type of special factorization in this section. Nothing that we've seen before. We know that a difference of squares is factorable. We know that a sum of squares is prime. Let's look at a sum and a difference of cubes, because it turns out they are both factorable. And I'm simply going to give you the pattern. I'm simply going to give you the formula. If you have a first cubed, let's say minus, I'm going to write that low because I'm going to come back and put a plus. Let's say I have a difference of cubes. A first cubed minus a last cubed. It turns out that this is factorable, and it factors as the first minus the last times the first squared plus the first times the last. Notice it's not double first last, it's just plain first times last, and plus the last squared. It also turns out that a sum of cubes is also factorable, and the change in our formula is here. That's a plus, but that would be a minus. She has these same rules for us in two separate boxes. Her difference of cubes on page 357 in terms of x's and y's, and the sum of cubes she gives on page 358 in the brown box in terms of x's and y's. I put it all together with plus minus notation, and I use F for first and L for last. A couple things to notice. The sign in this binomial will always match the sign of the problem. The first sign in this trinomial will always be the opposite of that. And this last sign is always positive, always plus. Now, I've seen some people say the first sign will be the same, because then they can spell something. Same, opposite, always, positive spells soap. And if soap helps you remember, well, use it. I will still continue to say match, opposite, always plus. But if you want to call it same, opposite, always plus, and remember soap, that works. And so what do we have? If I have a sum or difference of cubes, it will always factor as a binomial and a trinomial. The sign in the binomial matches the sign of the problem. The first sign in the trinomial is the opposite of that. and the last sign is always plus. And then I have 5 little blanks to fill in, and I fill them in with the first, the last, the first squared, the first times the last, and the last squared. So this is a pattern I need to, well, memorize. Hopefully you get into the rhythm of it and it just sticks in your head. But let's do a handful of these. This is a sum or difference of cubes. And I'm just going to grab number 84 from the homework. Do you have your handout handy so that you can see that list of perfect cubes? You need to get that memorized so you can spot these without your handout. The instructions read factor. And I see a binomial. Well, one thing I ask when I see a binomial is this a difference of squares? No, it's not. It's not a difference. It is a difference, but those aren't squares. Well, then maybe it's a sum or difference, in this case a difference of cubes. Is this a difference of cubes? Yes, it is. The first term is the cube of x, and the last term is the cube of 7. This is a difference of cubes. Well, then I know how that factors. It will factor as a binomial and a trinomial. The sign in the binomial will match the sign of the problem. The first sign in the trinomial will be the opposite of that, and the last sign is always plus. And now I fill in these 5 blanks. I fill them in with the first, that's x. The last, that's 7, right? The first, the last, now what? The first squared, x squared. Right here, the first times the last. X times 7 is 7x. And the last squared. 7 squared is 49. Please don't write 7 squared. That's not finished, and I will take points off for it. 7 squared is 49, so write the 49. And that's how this factors. Let's do another one. Let's have a look at number 86. I see a binomial. So the things that I ask myself will be, is this a difference of squares? No, it's not. Is this a sum of squares? No, it's not, and a sum of squares would be prime. Is this a sum or difference of cubes? Well, it's a sum, and it is a sum of cubes because this first term is the cube of p. This last term, 512, is 8 cubed. So I have a sum of cubes. I know how that factors. It factors as a binomial and a trinomial. The sign in the binomial will match the sign of the problem. Or if you're using SOAP, will be the same, opposite, always plus, right? I'm going to continue to say match, and my first sign of the trinomial will be the opposite of that, and this last sign is always plus. Then I fill in my blanks with the first, the last, the first squared, the first times the last, and the last squared. Again, don't make the mistake of doubling this first times the last. That has nothing to do with this kind of problem. So we fill them in. The first, that's p. The last, that's the 8. The first squared, p squared. The first times the last, p times 8 is 8p. And the last squared, 8 squared is 64. And that's factored. And by the way, this trinomial at the end, you don't have to worry about checking it. It will not factor any further. The trinomial that results from factoring a sum or difference of cubes will not factor further. Let's do one more. I want to do a very simple one just so that we have the ability to check it quickly, because I want to show you that this does work. Okay, let's factor, I'm just going to make one up. Let's factor x cubed plus 8. This is a sum of cubes. The cube of x and the cube of 2. It will factor as a binomial and a trinomial. The sign in the binomial matches the sign of the problem. The first sign in the trinomial is the opposite of that, and the last sign is always plus. We fill in the blanks with the first, that's x. The last, that's 2. The first squared, x squared. First times the last, x times 2 is 2x. And the last squared, 2 squared is 4. And this is factored. And if I want to check this, I'll do that by using term-by-term multiplication. Distribute this x to each of those, and come back and distribute that 2 to each of those terms in the trinomial. X times x squared is x cubed. X times minus 2x squared. And x times 4 plus 4x. Now go back and distribute this 2. 2 times x squared plus 2x squared. 2 times minus 2x minus 4x. And 2 times 4 plus 8. Combine like terms. We've got our x cubed. Now watch what happens. My square terms, they subtract out, don't they? My linear terms, well, look at that. They subtract out. To leave just this little guy at the end, I left my cube off my x, didn't I? X cubed. The square terms subtract out, the linear terms subtract out, and plus 8. And it returns that original binomial, that original sum of cubes that we factored. So it does work. Number 90. Now, if I just glance at this and I go, oh, there's an 81, that's a square. This is a sum. A sum of squares is prime. No. The rest of those aren't squares, are they? And before you jump on anything, what do you do first? First things first. You look for a greatest common factor. Between these two terms, greatest common factor is 3. So factor out that 3. 3 pulled out of 81 leaves 27. X cubed and plus, pull 3 out of 3, it leaves a 1. Now, are we done, or will this factor further? Well, let's see. Is this a sum of cubes that I have here in parentheses? Yes, it is. This first term is the cube of 3x, and 1 is the cube of 1. Don't forget your greatest common factor out front, and now we're factoring this sum of cubes, which will factor as a binomial and a trinomial. The sign in the binomial matches the sign of the problem. The first sign in the trinomial is the opposite of that. The last sign is always plus. Our 5 blanks. The first, 3x. The last, 1. The first squared, you square 3x, you get 9x squared. The first times the last, 3x times 1 is 3x. And the last squared, 1 squared is 1. This is now factored completely. Always look for that greatest common factor first. Let's finish up with one more. This is one, if you want to give it a try on your own, once we get it written down here, go ahead and pause, and then come back and we'll compare answers. The instructions simply read, factor. If you want to give that a try, go ahead and pause. We see a binomial, so we have some questions. First things first, though, we look for a greatest common factor. Between these two terms, is there any greatest common factor? If you've got your powers memorized, you recognize that 125 is just 5 times 5 times 5. And 5 is not a factor of 64. So there is no greatest common factor that I need to pull out. Now, seeing that this is a binomial, I have to wonder, is it a difference of squares that I can factor? Is it a sum of squares that is prime? Or is it perhaps a sum or difference of cubes? This looks like a sum of cubes because this first term is the cube of 4x. Very careful. 64 is a cube and a square. It's the square of 8, but it's the cube of 4. This last term is a cube. It is the cube of 5y. So this is a sum of cubes, and it will factor as a binomial and a trinomial. The sign in the binomial matches the sign of the problem. The first sign in the trinomial is the opposite of that. And the last sign is always plus. Then we fill in these 5 blanks. Have you gotten where you can do it without having that formula shown at the top of the board? We'll go in these 5 blanks. The first, the last, the first squared, the first times the last, and the last squared. Here we go. The first, 4x. The last, 5y. The first squared. You square 4x, square the 4, get 16, square the x, get x squared. Right here, first times the last, 4x times 5y, 20xy. And finally, the last squared. You square 5y, you get 25y squared. And that is factored completely. How'd you do? Now, I'm going to go ahead and tell you that when you get down to number 107, something interesting may happen. You remember when we did number 44? Number 44 was a difference of squares. We factored it, and we discovered another difference of squares and had to keep going. But keep that problem in mind when you try number 107. It might have something like that lurking in there for you. So I'll let you get going on this homework. Lots of practice. And then next time, we're going to put all 4 sections together and see what we can do.